So good afternoon. Today we are going to do the 11th week assignment or tutorials for the subject solid state operations. We'll be starting in 5 minutes. Okay, let's start. I've shared the screen. I hope it is visible. So the first question is, what are the advantages of nanoparticles? What are the advantages of nanoparticles? So nanoparticle means the particle size in nanometer range. That is very, very small particle. We cannot actually imagine or we cannot see even nanoparticles with our naked eye. So this type of particles has very much advantages. What is that? First one is the increased electrical and thermal conductivity. Second one is the lowered melting point. Third one, stronger mechanism or stronger magnetism. Fourth one, unique optical properties. And there will be many along with this. Okay, so these are the basic advantages of using nanoparticles. Next, what is the size of human hair? What is the size of human hair? The answer is 10 to 50 micrometer, or sometimes it is around 80 micrometer, around 100 micrometer also, but the average is between 10 to 50 micrometer. Next, what is the size of dendrimer? What is the size of dendrimer? So the dendrimer size is 1 to 10 nanometer. 1 to 10 nanometer. Next, what is the nanometer range? What is the nanometer range? So as we know, the nanometer range is between 1 nanometer to 1000 nanometer. Okay, this is the total nanometer range. Next, what are the 2D nano objects? What are the 2D nano objects? Nanodiscs and nanoplates. Nanodiscs and nanoplates are 2D nanoparticles. Nanotubes are 1D objects. Is it true or false? Nanotubes are 1D nano objects. Is it true or false? So, nanotubes as well as nanofibers are 1D nano objects. So, previously I have seen nano discs and nanoplates are 2D objects. Nanotubes along with nanofiber are 1D nano objects. So, it is true. Next, what is nanomaterial? What is nanomaterial? So here we'll see a video that how these nanomaterials are coming. So the video is about what is nanotechnology and what is nanomaterial. Nano means small, very small. It's a million times smaller than the smallest measure on a ruler if you want to get an idea of how small a nanometer really is. So, in a scale bar, if you know the smallest measurement and take 1 million of that, you will reach nanometer, right? That is how it is small. Okay. So now they are talking about the hair. So now take a good close look at the strand of hair. So if you see under microscope, what we'll see? To shrink down smaller pillars, smaller than the smallest thing you know. The naked eye, you find that your piece of hair starts to look lot more interesting. You are now about the size of a red blood cell. Your strand of hair is a massive tree compared to you, even at this size. You are still 1,000 times too big to be considered nano. To get you down nanoscale, you will have to shrink you about 100 nano tall. Do you understand that they are trying to quantify that how small a nanoparticle can be, how you can imagine it. That is how they are saying. So further, you see, this is the light is going. Light as our lights, you are now smaller than the. So here, lights, you are now smaller than the wavelength of visible light. You are practically invisible. But for the sake of demonstration, I think we should turn on some lights at this side of the red blood cell. So you have seen the red blood cell size, I think 2 to 5 micrometer, right? Yes, 2 to 5 micrometer. And now you are trying to quantify it. So you are saying that your red blood cell 1,000 times bigger than you are. It is like an enormous stadium. Welcome to the nanoscale. You could probably hold a common cold virus in your hands quite comfortably. Now, the rhinovirus is only about 30 nm across and is nearly impossible to see next to the red blood cell, and the red blood cell is too big to be considered nano. However, it's made up of all kinds of nanomaterials. If you were to look close enough, you would see that the outer walls of the cell are stabilized by a flexible mesh-like, you can see the mesh, right? Mesh-like protein skeleton. The bars and connections that make up this mesh are considered part of a nanomaterial. Without these reinforcing nanostructures, the cell would be much more fragile and not nearly as flexible. It wouldn't stand a chance in your body. So these nanomaterials, the mesh of the proteins in that nanomaterial, in this nano level red blood cell giving the support to be flexible. Everything is made up of nanomaterials. Nanomaterials are an arrangement of molecules and atoms that when combined create stable building blocks that can be made into larger, more complex materials and structures, which is pretty much everything, including this little piece of here, right? So these small nanomaterials make up bigger things like hair, which is still small in our eyes, right? So that is how nanotechnology comes into picture. So this is an just overview of nanomaterials. Next, what are 2D and 1D nanomaterials? What are 2D and 1D nanomaterials? So you have just seen the videos of every kind of nanomaterials. Now what are 2D nanomaterials? We have learned that it is nanodiscs or nanoplates, and 1D are nanotubes and nanofibers. So we'll see the videos one by one. Okay. So they are showing first what they are nanoparticles. But what is a nanoparticle and how has it influenced the science of modern world? Nanoparticle is an ultra-fine unit with dimensions measured in nanometers. Nanoparticles exist in the natural world and are also created as a result of human activities. Due to their submicroscopic size, they have unique material characteristics, and manufactured nanoparticles may find practical applications in a variety of areas, including medicine, engineering, catalysis, and environmental remediation. Nanoparticles can be classified into any of various types according to their size, shape, and material properties. Some classifications distinguish between organic and inorganic nanoparticles. The first group includes dendrimers. So, dendrimers is organic nanoparticles, right? Liposomes and polymeric nanoparticles, while the latter includes fullerenes, quantum dots, and gold nanoparticles. So these are inorganic nanoparticles. Fullerene, quantum dots are formed from carbon. Quantum dots formed from any kind of semiconducting material. Gold nanoparticle means it is made of gold. There are other type of nanoparticles like silver, any metal particle. If, in smaller size, you can call it nanoparticle. That is silver, platinum, silica, titanium, like this. And the organic nanoparticles are liposomes, which you will get in our body, right? Cool nanoparticle-based technologies center on opportunities for improving the efficiency, sustainability, and speed of already existing processes. Nanoparticles-based technologies use less material, a large proportion of which is already in a more reactive state. Other applications of nanoparticles are those that stem from manipulating or arranging matter at the nanoscale to provide better coatings, composites, or additives, and those that exploit the particle's quantum effects. Nanoparticles occur naturally in the environment in large volumes. For example, the sea emits an aerosol of salt that ends up floating around in the atmosphere in a range of sizes from a few nanometers upward, and smoke from volcanoes and fires contain a huge variety of nanoparticles, many of which could be classified as dangerous to human health. However, nanoparticles offer tremendous potential for new or improved forms of healthcare treatment that has produced a new field of science called nanomedicine. Okay, so this is what is nanomaterials. So this is the vast world of nanomaterials or nanoparticles. This is the purpose of nano discs. Okay, so membrane proteins are the key for communication between cells. Fundament they mediate fundamental biological processes such as signal transduction, transport processes across membranes, sensing of chemical signals, and coordination of cell-to-cell interactions. Right? Numerous diseases like the coronavirus enter human cells through membrane proteins. This makes them important target for drug development and an interesting object of research. Therefore, it might seem surprising that although 23% of the encoded human genes are membrane protein, they only represent 1% of known protein structure. Okay. However, it is not easy to separate a membrane protein from its cell membrane in order to analyze it. The reason for this can be found the reason for this can be the reason for this can be found in the structure of the cell membrane, right? This consists of a lipid. This how cells are formed. The cell consists of a lipid bilayer, which it made up of two rows of phospholipids. Okay, each phospholipid consists of a phosphate head, which is hydrophile linked to two fatty acids. Membrane proteins mimic these properties. Therefore, the surface of membrane proteins inside the hydrophobic core of the lipid bilayer are also hydrophobic. Those parts of the protein in contact with the aqueous membrane environment are hydrophilic. Okay. So lipid layer cells have lipids. Lipid layer are form of phospholipids and two bilayers of phospholipids, and that is how the cells are formed. Solubilizing a membrane protein in a standard aqueous buffer prompts the hydrophobic parts of the membrane protein to clump together. One can imagine this to function similarly into a micelle, where the hydrophobic tails of phospholipids turn inward to touch the water as little as possible, right? Because of surface tension. And the hydrophilic heads point outward. This alters the native structure and folding the membrane protein. In most cases, the consequence is that the membrane protein cannot be studied in its native from anywhere anymore. This is where nanodiscs enter the stage. So this is the why nanodiscs are important that they have shown here. Okay, now what is the improved strategy of the nanodisk? We will learn here on. Nanodiscs allow membrane protein to be removed from the cell membrane whilst maintaining their okay, original physiological property. Additionally, nanodiscs are highly soluble in aqueous solutions, which allows the membrane proteins inside them to be kept in a solution without detergents. With the help of nanodiscs, membrane proteins can thus be studied in a native-like environment. So this is the importance of nanodiscs. The term nanodisk describes a disc-shaped structure that is able to stabilize membrane proteins by using a belt. This enables membrane proteins to maintain their folding after being removed from the cell membrane. Some nanodiscs are also contain a core of phospholipids, which can be either be of artificial origin or originate from the cell membrane itself. The two main categories of nanodiscs are membrane scaffold protein nanodiscs, or in short MSP nanodiscs, and synthesis nanodiscs. In accordance to their names, MSP nanodiscs are held together by membrane scaffold proteins, whereas synthetic nanodiscs use a synthetic belt. Okay. If you are interested to see how a synthetic nanodisc can be used, you can see the further videos. Yeah. So this is the nanodisc comes to give the support to membranes. Third one is a different kind of nanomaterial, which is nanotubes or carbon nanotubes, which are one-dimensional nanoparticles. This is the shape of carbon nanotubes. This is Carbon nanotubes are what? Allotropes of carbon with a cylindrical nanostructure. Okay. So you can see how they are forming a cylindrical structure made by graphene sheets rolled up through processes such as chemical vapor deposition or discharge, arc discharge. So graphene sheets roll into form carbon nanotubes. So these are the properties of carbon nanotubes. First one is the mechanical property. Second one is electrically they are very sensitive. And third one is the thermal. So this is the strongest and stiffest material yet discovered. Okay, among the nano in the nanotechnology. So nanotubes have multiple applications: air and water filtration. Okay, they can be used in energy storage, biomedical applications for heat sensitivity, fiber and fabrics, bullet proofing materials, and composite materials. So this is the nanotubes, 1D nanotubes. Last one is the nanofibers. This is the nanofiber. So this is the nanofibers. So this is the nanofiber. You cannot see there with naked eye. So this is a filter. So it is going inside it, and now you can see the nanofibers. This is the nanofiber. So now when bacteria are going there, electrically charged in a high voltage. So the process is the starting point in making drop of a polymer solution is the starting point in making nanofiber. The drop is electrically charged in a high voltage electric field to give birth to nanofiber. The fibers are laid over each other, resulting in a nanofiber that you can get in an idea of the small size nanofiber by comparison with bacteria which are unable to penetrate through a nanofiber mat, as the pore size of the mat is much smaller than the size of the bacteria. Nanofibers are thus capable of protecting against bacteria and viruses. In uh, a nanofiber membrane can stop water from passing through such a uh, clothes. Drop of water slip away on the mat surface. However, textile materials of nanofibers are very breathable because air molecules can get through the same membrane easily. For example, a nano from breathing thus prevents being inhaled by the less comfortable chemicals. Hundreds of nanofiber applications owing to their specific characteristics. Nanofibers are revolutionary material for the third millennium. Okay, proceeding to the next question. Explain the types of nanoparticles. Explain the types of nanoparticles. So, first one is the based on size. Based on size, shape, and material properties. Under this comes different shape, that is zero-dimensional nanoparticle, 1D nanoparticle, 2D nanoparticles, sheet, 3D nanoparticles, etc. Okay, so under 0D comes Q dots, fullerenes, and gold NPs, gold nanoparticles. Under 1D is carbon or metallic nanotubes. Gold nanowires, also there in 1D polymeric nanofibers, metal nanorods. Under 2D nanoparticle comes carbon coated nanoplate, carbon coated nanoplates, graphene sheets, layered nanomaterials. And third 3D nanoparticle is bulk nanomaterials, polycrystals, liposome, polycrystalline and dendrimers. Okay, so this one is the based on size. Second comes based on organic or inorganic. Organic and inorganic. Under this under inorganic comes gold nanoparticles, quantum dot, iron oxide nanoparticles, lanthanide ions, and under organic nanoparticles comes dendrimers, micelles, liposomes, etc. Okay. So so this is the second one. First one is the based on size, shape, and material properties. Next one is the organic or inorganic. Third one is the based on carbon, ceramic, semiconducting, or polymeric. So under this comes carbon nanotubes, that is CNTs and fullerenes. Fourth one is the hard to or hard or soft particles. Under these hard particles comes titania, that is titanium dioxide, silica dioxide particles, and fullerenes. And under soft particles comes liposome, vesicles, and nanodroplets. Okay, so these are the basic classifications of gold nanoparticles. Next, nanomaterials have same properties as of bulk materials. Is it true or false? Nanomaterials have same properties as of bulk materials. Is it true or false? The answer is false, because nanoparticles or nanomaterials properties are very different from the bulk. Okay, so they can never be same, because nanomaterials and nanoparticles are very sensitive compared to the bulk materials. So the properties have to be different. Next, the atoms or the molecules at the surface are more active than those inside the solid particles because of easy bonding with contacting material. Is it true or false? So from the name itself, it is clear that from the question itself, it is clear that it is true. The atoms or molecules placed at the surface have to be more active because they are contacting with other materials easily and they are creating some bond. Next, as the micronization of solid particles, the specific surface area increases generally in dash proportion to the particle size. So as the micronization of solid particles, the specific surface area increases generally in. The answer is reverse. The answer is reverse. So that means as the micronization of solid particles, that means the big material getting chopped and producing small nanoparticles or solid particles. The specific surface area increases generally in reverse because specific surface area expression is S equals to 6 by rho L. Rho L is the size, particle size, so it is oppositely proportional. Amorphous particles usually adopt a dash shape. So amorphous particles usually adopt a spherical shape, which is very normal. Any part shape gives minimum or maximum surface to volume ratio. Sorry, maximum surface to volume ratio, right? The amorphous particles usually adopt a spherical shape. Next, which nanoparticle has highest aspect ratio? Nanotubes and nanowires with various shapes such as helixes, zigzags, belts, or perhaps nanowires with diameter that varies with length. These nanotubes and nanowires have high aspect ratio. Next, which nanoparticle has small aspect ratio? High aspect ratio means their length is very high, greater than to their diameter, right? Next, which nanoparticle has small aspect ratio? Which nanoparticle has small aspect ratio? The answer is spherical, oval, cubic, prism, helical, or pillar. Collections of many particles exist as powder, suspension, or colloids. That is, their aspect ratio is very small. The melting point of the nanomaterial, the melting point of the nanomaterial is from that of the bulk material. What will be in the gap? The answer is decreases. The melting point of nanomaterial will be decreased from that of the bulk material, obviously. So the answer is decrease. Next, what is the relation between dielectric constant and particle size? What is the relation between dielectric constant and particle size? So, dielectric constant tends to increase considerably as the particle becomes smaller than about 20 nanometer. This is particularly saying for a material which is PbTiO3. For this particular material, they are saying that dielectric constant increases or tends to increase considerably as the particle becomes smaller than about 20 nanometer, sorry. In general, also dielectric constant increases with uh, smaller particle size. Okay. Next, what is the critical size of BaPbTi compounds? Barium, lead, and titanium compounds to keep the ferroelectric property. What is the critical size of BaPbTi compounds to keep the ferroelectric property? The answer is 317 nanometer, right? 317 nanometer. Next, what is Curie point? What is Curie point? The Curie point is defined as the point. The Curie point is defined as the point changing from the ferroelectric material to the paraelectric phases of PbTiO3 reduces drastically with decreasing particle size below 20 to 30 nanometer. So for this PbTiO3, the Curie point is defined as a point changing from the ferroelectric material to the paraelectric phases drastically, reducing drastically with decreasing particle size below to 20 to 30 nanometer. This is the Curie point. Next, what is ferroelectricity? What is ferroelectricity? So we'll see a video here. So now they are saying that what is ferroelectricity? So they are showing three type of electricity here, difference between three type of electricity. First one is the pyroelectricity. Pyroelectricity is the ability of certain materials to generate a temporary voltage when they are heated or cooled. The change in temperature modifies the positions of the atoms slightly within the crystal structure such that the polarization of the material changes. Okay. Pyroelectric crystals can be regarded as having a built-in or permanent electric polarization. So this is the pyroelectricity. So it possesses or it generates temporary voltage when they are heated or cooled, because during the temperature change, the positions of the atoms slightly shifts within the crystal structure such that the polarization of the material, changing the polarization of the material. Okay. So this is the pyroelectricity. Next one is the ferroelectricity. Ferroelectricity is a phenomena where spontaneous electric polarization of the materials takes place. The reverse electric polarization is possible by applying an electric field. So, what is it saying? Ferroelectricity is the phenomenon where spontaneous electric polarization of the material takes place. The reverse electric polarization is possible by applying an electric field. Ferroelectricity was discovered in 1920, and Rochelle salt exhibited the properties of sudden electric polarization. Since its discovery, various uses have been devised, and today ferroelectricity is used in various fields of electronics or nanotechnology. The materials exhibiting the phenomenon of ferroelectricity are called ferroelectric materials. Ironically, the ferroelectricity or the ferroelectric materials do not have any connection to iron. Okay, it's ferroelectricity does not have any connection with the iron, but from the name itself you can think that it is a kind of magnetic property or something, but it is not. So ferroelectricity is phenomenon where spontaneous electric polarization of the material takes place. And what about the pyroelectricity? Pyroelectricity, we have learned that it is the spontaneous or it is the sudden polarization due to or temporary voltage or polarization due to the heat or heating or cooling. Next is the piezoelectricity. So piezoelectricity, also called the piezoelectric effect, is the appearance of an electric potential, a voltage in other words, across the sides of a crystal when you subject it to mechanical stress or by squeezing it. In practice, the crystal becomes in practice the crystal In practice, the crystal becomes a kind of tiny battery with a positive charge on one face and a negative charge on the opposite face. Current flows if we connect the two faces together to make a circuit. In the reverse piezoelectric effect, a crystal becomes mechanically stressed, deformed in shape when a voltage is applied across its opposite faces. So, see the difference. Piezoelectricity is about the voltage generation due to temperature and due to temperature change, right? It is either heating or cooling. Ferroelectricity is about the spontaneous voltage generation or spontaneous polarization. Piezoelectricity is about the generation of electric potential or voltage when you're subject to mechanical stress. Okay, so these are three different types of electricity generation process. For pyrrhicity, it has a unique polar axis, which means polarization is along a certain axis, and this polar axis may or may not be reversible by reversing the direction of applied field. Pyroelectrics also exhibit non-centrosymmetry. Ferroelectric materials can be easily polarized even by a very weak electric field, and these materials have spontaneous polarization. They also have permanent electric dipoles and internal electric field which develop spontaneous polarization. Okay, that is why they are spontaneously polarized. And they exhibit non-centrosymmetric symmetry. Non-centrosymmetry is the point groups that lack an inversion center. They are non-polar dielectric group. Piezoelectric effect is due to creation of electric charge by the applied stress, where D is piezoelectric, P equals to D sigma, where D is piezoelectric coefficient and sigma is the mechanical stress. So this is the basic differences of piezoelectric materials or ferroelectricity, piezoelectricity, and pyroelectricity. Next, we will see different properties of nanomaterials. What are the different properties of nanomaterials? So we know there are thermal properties, electrical properties, optical properties, mechanical properties, etc. Right? Now we'll see them one by one. So this is a big video where it is saying about the all kind of properties. Okay, so we'll see. Nanoscience, in today's episode, we will take a look at what nanoscientists actually encounters when they succeed in obtaining materials with building blocks only 10 times larger than an atom. It is now time to understand why nanomaterials are so starkly different from their bulk or larger sized counterparts. If I read this, we will get to know the whole lecture will be visible to your eyes. This is a very beautiful video. Their bulk or larger sized counterparts. Here we find Here we finally make some progress in understanding the mysteries behind the strange properties behind the Hypergas cup and Damascus steel, which we have discussed in brief on our page. We also try to understand why gold is yellow, but a solution of suspended gold nanoparticles can have colors ranging from violet to wine red. Right. Or why graphene, which is essentially only a flat sheet of carbon atoms arranged in regular repeating hexagonal pattern, is potentially 10,000 times stronger than steel and can conduct heat about 7,000 times better than metallic copper. So now the property analysis will come and everything will be very clear. When one deals with objects at the nanoscale, one must all but forget what that material behaved like when it was still in the millimeter or micrometer size range. The two main factors that come into play now are the quantum confinement effect and the drastically altered surface to volume ratio of the atoms that make up the material. These two effects and their unique interplay is the reason that nanomaterials are sought after for their novel and enhanced properties. Okay, so these two properties are very important for nanomaterials: quantum confinement effect and surface to very high surface to volume ratio. Okay, but to regular materials. Let us start by understanding the meaning of the surface to volume ratio. In simple terms, it is a mathematical term where the surface area of an object is divided by its total volume to arrive at a mathematical quantity indicative of how much of the material that makes up the object is occluded from external interactions. Naturally, the higher this ratio, higher is the amount of material that can interact with its environment. As an example, let us consider small cubes having an edge length of 1 centimeter, which gives them a surface area of 6 square centimeters, right? This type of lecture is there in the chapter in the science note also, but it will be very much more clear because it is visible to your eyes from this lecture. And a volume of 1 cube centimeter, giving object a surface by volume ratio of 6 per centimeter. Imagine a slightly larger cube object B made of the smaller cubes where its edge length is 2 centimeters. This means that a surface area of 24 square centimeter and a volume of 8 cube centimeters gives object B an surface to volume ratio of 3 per centimeter. This means that a reduced amount of material is available to interact with any external factors. As the cube's edge length goes on increasing, the surface to volume ratio will decline and so will the expected interaction capability of the object. Why this phenomenon is important for nanomaterials is that if we talk about the atoms or molecules that make up nanomaterials, instead of talking about little cubes, we will arrive at the same conclusion as before. This factor alone is enough to make the behavior of nanomaterials drastically different from bulk material. But it is not the only factor in play. You see, when you deal with atoms, you can't ignore their cousins, the electrons. At a size scale of only 10 times larger than an atom, we are still in the mysterious quantum realm, and when in Rome, we must do as the Romans do. In our everyday life, we have heard of objects being electrical, conductors, insulators, or semiconductors, which simply tells us how easy it is for electrons to flow through certain objects or materials. What decides the properties of these materials are their building blocks, that is, the atoms they are made of. An atom They are made of an atom is essentially made up of a central core called the nucleus, which is formed by neutral neutrons and positively charged protons. Around this core, electrons move in orbits of sequentially increasing radius. All the elements have different numbers of electrons orbiting the nucleus, which gives them all their different properties. The electrons in the outermost orbit are called valence electrons, and these primarily interact with whatever the atom comes into contact with. When an atom is given energy in any form, electrons from this valence shell jump to an imaginary level of higher energy called the conduction shell. So we will know what is here. Depending on how many electrons can enter this conduction band, a material may be classified as a conductor, a semiconductor, or an insulator in decreasing order of electronic activity. When we talk about a thing, these things you know already, but when you are reading for another time and visualize and try to connect with nanotechnology, nanomaterials, why these are important, you will the vision will be clear. So electronic activity, when we talk about a single atom, these various electron orbits and the valence and conduction levels can be thought of as different energy levels, with the innermost electron orbit having the highest stability and thus being lowest on the scale, and the conduction level having the lowest stability and being highest on the scale. When we talk about a number of atoms, these energy levels of many atoms seem to merge and form bands with all energy levels of similar energy almost overlapping each other. See? Thus, the gap between the valence band and the conduction band, hereafter called the band gap, is the factor that decides how much energy is required to allow electrons to start moving through the material. Right? Insulators have the highest band gap and require extreme amounts of energy to allow the flow of electrons, which may even damage material. Conductors have the lowest band gap, which means that small amounts of energy are enough to allow the flow of electrons. Semiconductors have a band gap between those of insulators and conductors. This theory of bands makes it very easy to study the properties of bulk materials that have extremely large number of structural units, since their energy levels merge conveniently to form bands. But when we talk about nanomaterials, since there aren't enough structural units to properly merge into bands, the properties differ vastly from bulk materials. When you go top down, the bands move away from each other, making electrical conductors into semiconductors or insulators. And when you go bottom up, the opposite trend is observed. Since the large scalar bulk properties are confined due to the proximity of the bands as measured in the quantum realm, this is called the quantum confinement effect. Okay, so that means when the particle size is top down, that is becoming smaller and smaller and smaller, the conductors are becoming converting into semiconductor as well as sometimes to insulator. This is the quantum confinement effect. Thus, the surface to volume ratio and quantum confinement effect together dictate the properties that any given nanomaterial will have. These are seen in some very interesting ways that completely defy common expectations. Optical properties of nanomaterials. As discussed before, the gap between the valence and conduction bands increases as we go from bulk to nano. That is, the band gap increases and it takes more and more energy to excite an electron. As an example, okay, I think the video is clear as I am reading simultaneously. Okay, so let us think back to our gold solution. In the visible spectrum, that is in the vivid iode range of colors, violet has the shortest wavelength and red has the longest wavelength, right? If you look at the equation on the screen, you will observe that wavelength and energy of the photon are inversely related. Therefore, a photon of the violet color will have the highest energy and the photon of the red color will have the lowest energy, right? One thing we must remember is that the color that we see is the wavelength that an object reflects. So this is very common, right? So that is also coming from that why the sky is blue. Sky is blue because all other colors in the VGR or all other rainbow colors, the sky where the particles, dust particles, different type of gas particles, clouds are there. They are absorbing all other particles, but they reflect back the sky color. Blue color they reflect. That is why we see the sky as a blue. So it is what this is telling that an object reflects. So the color that we see is the wavelength that an object reflects, while the remaining wavelengths are absorbed. Therefore, going back to the band gap theory, it is expected that when gold goes from bulk to nano, its band gap will increase. Obviously, this is a avid. So you can see this is the color of gold nanoparticle solution. But what do we know? The gold nanoparticle is a golden, right? We expect it to be golden, but gold nanoparticle solution is of violet to wine color. The band gap will increase as the gold will go from bulk to nano. This is evident because bulk gold is yellow, which you can see here. The bulk gold is yellow, which means a medium energy, and gold nanoparticle solutions have either a wine red or violet color, which clearly shows a shift from Y to V on the Vibgyor scale, which shows an increase in the band gap. That it is going to the left. That means it is going to the higher energy state. That means why high energy? Because the band gaps is too much high here between the valence band and conduction band, right? Increase in the band gap and a consequent increase in the energy required to excite an electron. So again, if we repeat this thing, bulk gold is yellow, which means a medium energy, and gold nanoparticle solutions have either a wine red or violet color, which it is not pure red, it is wine red, which clearly shows a shift from Y to V on the Vibgyor scale, which shows an increase in the band gap and the consequent increase in the energy required to excite an electron. Another amazing example of this phenomenon is butterfly. butterfly wings, which appear to be shimmering and multicolored due to their nanoscale structural units. Second property is the electrical and magnetic properties. The properties of nanomaterials is the second one. Now that we have studied the quantum confinement effect and seen its implications in everyday life, understanding the electrical and magnetic properties of nanomaterials will be easier. The band gap theory very concisely explain why metals which are usually conductors may become semiconductors or even insulators at the nanometer size scale. However, this phenomenon can be finely tuned by doping other atoms in a nanomaterial or by controlling its size and shape called its morphology. This allows the band gap to be controlled and influenced as per the need of any particular application. This strategy is frequently used in the design of modern types of solar cells, such as dye-sensitized solar cells and quantum dot sensitized solar cells. Among others, the case of magnetic properties follows similar lines but is influenced by some more complicated factors, such as change in orbital configurations of electrons, change in electron spin activity, etc. These properties also depend on the polarizability of the nanomaterial, which can be altered by doping and morphological control. Often exotic states such as superconductivity and historic applications such as exploratory research can be easily accessed by unique and ingenious material design strategies. Nanomaterials have been integral to the technological boom of the new millennium with their ubiquitous presence in circuit boards, display systems, high-end research aids, and many, many more physical and chemical properties of nanomaterials. Third one. When we talk about the physicochemical properties of nanomaterials, we must discuss the quantum confinement effect, QCE, and the surface volume ratio, SVR, together. While the QC dictates the electronic response to external stimuli, the SVR decides how many atoms or molecules are available for this interaction phenomenon. The SVR often helps in predicting the reactivity of a particular nanomaterial and is very useful in the design of nanoscatalysts. It can also be used to investigate whether or not a particular nanomaterial will be structurally stable and hence can predict the feasibility of a particular synthesis process. The SVR can also be used to study the porosity or orientation of nanomaterials so that their properties can be reliably predicted and corroborated after experimentation. The QC is vital The QCE is vital to most physical properties, such as electrical and thermal conduction, polarity and polarizability. The SVR and QCE phenomena together dictate the density, hardness, solubility, and surface energy of the synthesized nanomaterials. In the real world, this translates to all the possible applications that a material may have or the changes that need to be made in a material to achieve the desired properties. The properties of the nano world are as numerous as they are diverse, and yet there remains much still to be discovered. There remains. But it is only by shifting from macro to micro and micro to nano that humans have entered this era of technological progress, and it is only by exploring the sea of scientific mystery that we will be able to move even further. It's been a long journey so far, but sadly we haven't even begun to touch the tip of this iceberg that is the world of nanoscience. So this is the world of nanoscience and the properties of nanoparticles. I think it is clear. Next comes individually. I will see you. I will show you the photothermal properties of nanoparticles used in theranostic cancer therapy. So nanoparticles have unique properties with the potential to diagnose and treat disease at the same time. Okay, this is a Zika virus, this is 10 nanometer. Here is a virus for size comparison. Nanoparticles can be engineered to target disease tissue. Nanoparticles injected into the bloodstream can accumulate in disease tissue such as cancer. For cancer therapy, the nanoparticles diffuse into tumor tissue and are engulfed by cancer cells. Tumors containing nanoparticles usually appear very bright in CT scan, MRI, and ultrasound images, helping surgeons treat the right area. Okay. Once a tumor is located, much more intense beams of light or magnetic fields can be applied. The energy is absorbed uh, permanently by the nanoparticles, heating up and killing cancer cells. Scientists and clinicians are working hard to make this treatment a reality. In the future, so this is a model diagram. In the future, scientists hope to design intelligent nanorobots that can communicate with each other, beam information about the body to the outside world, and repair diseased cells. So this is the future of nanoparticles or nanotechnology using nanoparticles. How interesting it is, no? This is the electrical properties of nanoparticles. Or it is showing in particularly polymer-based nanoparticles. Electronic band structures. So you have just seen in that video that what are the electronic properties. Electrons are free in 1D and restricted in 2D. Principal quantum numbers. This is the 2D materials. So this is all about the conduction band, valence band, and the band gap. So we have seen that as the particle is going to the nanometer region, their band gap increases. That they need more energy to excite. This is the optical properties. Optical property also we have seen just. So macro, you can see the macro, this is gold color, but in nano, this is red solution. So here, if you just see this window pane in a church, or everyone have seen this kind of paintings in a church or anywhere in the place, any place. So you never knew that it is the gold, which is almost all the colors have been got. So these are painted with gold nanoparticles of different size. That is why the different painting color is formed. You can observe your red, yellow, green, blue, all these things are due to different particle sizes of gold and silver. These are the images of gold and silver nanoparticles. So if you just see here, the shape and size of the nanoparticles are different, giving rise to, you can get it from silver at 100 nanometer, gold at 50 nanometer would have behave like, appear like green in color. So therefore, the optical properties of a nanomaterial depend on the size and shape of nanoparticles. A reduction in size can lead to creation of surface plasmons. These plasmons have the ability to absorb light energy, which can give rise to different colors of nanomaterials. And therefore, as the size reduces, we have got different colors here. We have three categories of materials. The first three are the syllabus next to your goal and next day or silver code. Here, even though the composition of first you are same, it appears different in color because of the nanoparticle size, and hence proving this is laboratory, and hence this is proves how the optical property varies with respect to the particle size. That is when it becomes a nanomaterial. Okay, this is the property of nanomaterial. This is the mechanical properties of, and so you know mechanical property is related to the surface to volume ratio. Describes the relationship between the surface area and volume of a given object. Nanomaterials have relatively large surface areas while occupying relatively small volumes, resulting in high surface to volume ratio. The higher the surface to volume ratio, the more atoms are located on the surface of the nanomaterial, and the smaller the number of core or inner atoms located under the surface. To demonstrate how this works, let's imagine an aluminum cube of centimeter, so you can understand it. Volume value is 0.6 reciprocal centimeters. Now imagine into a flat sheet measuring 0.1 millimeters thick. The same volume of material now have much larger surface area. In fact, one sheet has the 2200 reciprocal centimeter, and then the same atoms arranged in cube. If you continue to stretch this until its thickness was at the nanoscale, its surface to volume ratio would continue to skyrocket, meaning most of the is on the surface and the very little volume. Carbon nanomaterials provide an extreme example of this. All of atoms in a buckyball or a sheet of graphene are surface atoms. This is no core volume. This is important because the dominance of surface is one unique characteristic of nanomaterials that gives rise to their novel behaviors and properties. By understanding materials with a high surface to volume ratio, We can design the techniques that the world so desperately needs, like high capacity batteries and seawater desalination systems. So this is how important the surface to volume ratio and quantum confinement effect is. Next, what is surface plasmon resonance? So it associates with the optical property of nanoparticle. What is surface plasmon resonance? So this they will tell the what is surface plasmon resonance. Surface plasmon resonance is an optical technique used to study and measure molecular interactions in real time. Okay. When the light moves from a denser medium to a light medium, such as from glass to air, it moves away from normal and at an angle greater than critical angle, it undergoes total internal reflection. You know these things, right? When light passes through from higher density zone to lower density zone, it goes away from the normal, and at certain critical angle, mm, total reflection happens. Now, for a plane polarized light undergoing total internal reflection, if a thin metal is placed on the top, then some sort of the refracted light is absorbed. As a result of this absorption, a dark zone appears in the refracted light. This absorption of light is carried out by the electrons present in the metal. Because of absorption of energy, the electron starts oscillating. Remember, it is not a single electron, but a group of electrons collectively absorbs the energy of light. These group of electrons undergoing oscillation because of energy absorption is called the plasmon. Understood? Yes. Now, the surface plasmon resonant angle depends on the refractive index of the medium near the metal surface, and any change in the refractive index near the metal surface will cause change in SPR angle. So you can see how the band gap is changed, how the energy absorbed is changed. Application is study interaction between two molecules. For example, the interaction between ligand and its receptor. The interaction between ligand and its receptor can be easily detected just by measuring the change in SPR angle. In a similar way, its option of biomolecules on a surface interaction between DNA and RNA can also be detected. So this is your surface plasmon resonance. So when some light passes through a metal, the group of electrons get excited and they start oscillating with the wavelength of the incident light, and due to that they give a advanced response in the detector. So that is the surface plasmon resonance. The hardness of the crystalline materials generally increases with decreasing crystalline size. Is it true or false? The hardness of the crystalline materials generally increases with the decreasing crystalline size. Is it true or false? The answer is true. So the hardness will also increase as the crystalline size of the particles will be in the nano size. A remarkable decrease of the contact angle is observed when particle radius is less than what? A remarkable decrease of the contact angles is observed when particle radius is less than 10 nanometer. What is the value of specific surface area? What is the value of specific surface area? The value of specific surface area is S into 6 by rho L. Rho is the density of the material and L is the length of that cube. Next, the dash of nanoparticle remarkably increases with increase in the surface energy of particle by the nanosize effect. The dash of the nanoparticles remarkably increases with increase in the surface energy. What is increased when the surface energy of a particle is increased? The cohesion between the nanoparticles increases with increase in the surface energy of particle by the nanosize effect, and that is how they form a composite nanostructure. Define the classification of composite structure of nanoparticles. Okay, so first one is the composite structure formed using nanoparticles or using nanoparticles. Example is core shell structure. That means it has a core inside it and of different materials, shell is there at the outside. Second one is the internal deposition or internal dispersion. Third one is the hollow. That means there is nothing inside it. And fourth one is the porous. Second one is the nanocomposites form from agglomeration of nanoparticles. Agglomeration of nanoparticles. In this way also core shell can be formed. Internal dispersion is there. Then agglomeration of particles are there. Coating is there, coating of the surface. Then hollow and porous. Fourth one is the composite structure body fabricated from nanoparticles. This is the nano-dense body. Nanoporous body. And nano-thin film. Okay, so these are the different structures of composite nanoparticles. Next, what is core shell nanostructure? What is core shell nanostructure? And how they are formed and used. Core shell nanoparticles are used in bioimaging. Okay. In general, the simple nanoparticles which are made from a single material, whereas these homicides or core nanoparticles which are composed of two or more materials. Core shell nanoparticles are found on two materials. Nanoparticles that consist of a core that is intermittent, TD, and a shell that is outer line material. We broadly defined as comprising a core inner material and a shell outer material. Like in course interactions, like in inorganic material. So this is a different type of core shell materials formed, synthesized. So different kind of nanoparticle that is so spherical, and a particle external also is a sphere. Second one is the hexagonal shape. Third one is the multiple particles of in the core and one cover is from the outside. Second one is the two core shell. And third one is there is a particle, then around it there is a hollow, and then there is a shell. So this is the different types of core shell particles formed. And how they are formed? They are formed by chemical synthesis, chemical vapor deposition, laser induced assembly, self assembly, colloidal aggregation, film deposition, and more. And now we'll tell the importance of core shell nanoparticles. Importance of finely functional material with modified properties. So some of the modified properties are less toxicity, cytotoxicity, bio and cytocompatibility, better conjugation with other bioactive molecules. These are the advantages of core shell nanoparticle. It also increases thermal and chemical stability and dispersibility. So you can see that how these are. So in the middle that is nanocore and the outside that is a shell. And in that shell, different type of application you can do. So it can be modified with fluorescent dye, drug payload, shell coating and surface modification, target ligand, drug or therapeutic inclusion, radionuclide, then MRI contrast motif, receptor ligand interaction, anything protein, amino acid, anything you can fix on that shell. So this is also used in bioimaging, that is in MRI. Okay, so we'll not get into that much. But this is how the core shell colloids are formed. Write about the applications of nanoparticles. So they are used widely in all fields in our everyday life. That is in cosmetics and sunscreens. Second one, used in electronics, forming electronic chip, electronic circuit. Actually, gold nanoparticles, nanomaterials revolutionized the circuit-based industry, right? LED, LED, then the small smartphones we are using everywhere there needs to adjust smart chips, which are all formed with the nanoparticles. Third one is the catalysis. Fourth one is the medicine. Nanomedicine are very popular right now, and this is where the cutting edge research is going on. Fifth one is the food industry, construction industry, environmental remediation, renewable energy, solar cells are made, then biosensors, which are very, very important. What nanoparticles are used in modern LED displays? What type of nanoparticles are used in modern LED displays? So, nanocrystalline, lead, telluride, cadmium sulfide, zinc, selenide, and sulfide are used in the light emitting direct LED modern displays. Okay. Next, what nanoparticles are used in site-specific drug delivery? What nanoparticles are used in site-specific drug delivery? So, Fe3O4, iron oxide, gamma Fe2O3, and supermagnetic iron oxide nanoparticles, that is called as PIONS, are the main nanoparticles used for the site-specific drug delivery. Okay. Next, nanoparticles have sterilizing and anti-fouling properties. Which nanoparticles have the sterilizing and anti-fouling properties? So titanium dioxide, and here is written titanium dioxide TiO2 nanoparticles are used in sterilizing and antifouling properties. How nanoparticles are made? There are two processes, right? Top-down and bottom-up method. In the top-down methods, bulk material is physically broken down to make smaller molecules. It is also called dry production method. And in the method, milling, laser ablation, and sparks ablation are used. And bottom-up method approach relies on nucleating atomic-sized materials into the eventual nanoparticles. It depends on the material being generated. It is also called wet production method. And the methods are called Starkevich method, citrate reduction method, gas phase synthesis, block copolymer synthesis, and microbial synthesis. Okay. So we'll see here how the nanoparticles are synthesized. So this is the bottom up and top down approach. So bottom up approach, nanoparticle clusters from atom nanoparticles clusters are formed atomic level, and from the bulk material is fragmented. Top down approach, from bulk material it is fragmented and form the nanoparticles or nanostructures. Okay, right? This is the basic differences of top down and bottom up method. Next, how nanoparticles are made physically. So physically there are processes like dry synthesis process, where ball milling, mechanochemical method is used, ball mills are used. In the and dry synthesis process, there are also three phases, three methods or three ways. First, in the mechanical, there is ball milling. So under the mechanical, you can say it is ball mill. Another one is the mechanochemical method, severe plastic deformation, cryomilling. Okay. For gas phase synthesis, there is inter-gas condensation, aerosol spray, pyrolysis, combustion, flame synthesis, plasma spray, chemical vapor deposition, chemical vapor condensation, evaporation techniques, atmospheric pressure electrical discharges. And under the other section, it comes the cryomelting, laser pyrolysis, reactive plasma arc evaporation, epitaxial growth, rapid quenching, solidification, ion beam sputtering, hydrogen reduction, etc. There are many. Okay, so these are main methods of producing nanoparticles in a top-down approach, that is physical methods. Next one is the how chemically they are formed. In the chemical methods, this is also called weight-based approach. Weight-based approach. So under the chemical method comes polyol method, then thermal decomposition method, then photochemical reduction method, then microemulsion method, hydrothermal, metal vapor synthesis, sol-gel method, sonochemical reactions, the sound and chemical are there, and electrochemical synthesis, electric field or chemical synthesis. So these are the methods of producing nanoparticles chemically. Next question. What is gas synthesis of nanoparticles? So under the gas synthesis, I have said already, there are two categories. First one is to fabricate nanoparticle, the first category consists of solid precursors used. Here, so under the first category, solid precursors are used. That is inert gas, condensation, laser ablation, spark, discharge, okay. And under the second category, it comes liquid and vapor precursor. First one is the solid precursor, second one is the liquid and vapor precursor. So it is solid precursor and it one is the liquid and vapor precursor. So here what is needed? Combustion flame synthesis, then spray and laser pyrolysis, flame pyrolysis. There is also plasma processing, etc. Evaporation techniques. Okay. So this comes under gas phase synthesis. Chemical vapor deposition also comes under the gas phase synthesis of nanoparticles. What is the chemical vapor deposition method? Here the method involves a chemical reaction. The method involves one or more volatile precursors. The substrate is exposed to those precursors that decomposes on it and form the desired deposit. The vaporized precursors are inserted into a CVD reactor or deposition reactor and absorbed onto a substance being placed at high temperature. So we can see one chemical vapor deposition method. So in this video you can see chemical vapor deposition method. This is the nanofabrication technique, the chemical vapor deposition technique or CVD. Used to deposit thin layers of materials or films onto a base material called a substrate. These processes, like many other nanofabrication processes, are highly sensitive and must be carried out in a chamber that is isolated from external atmospheric conditions and contaminants at very low pressure inside a vacuum. There are two types of vapor deposition processes: physical and chemical vapor deposition. It is important to be able to distinguish the difference between the two, but for now, let's focus on the core principle of vapor deposition process. The thin film is deposited on a base material called a substrate, such as glass or silicon wafers. In theory, any material can have a thin film deposited onto its surface. The substrate is essentially a foundation on which we will deposit the thin film. Designing and executing a vapor deposition process requires careful consideration of materials and equipment to ensure compatibility of the system. The substrate is then exposed to one or more vaporized sources. The presence of the vapors along with other stimuli will cause a thin film to deposit on the surface of the substrate. The type of thin film that will deposit is dictated by the chemistry of the vapors. Now that you know the basic idea behind vapor deposition, let's talk a little bit about why it's important. Thin films deposited through processes such as vapor deposition have their own unique properties. We may use these films to enhance or improve the original substrate material or use the film as a component part of a composite structure. This makes it possible to engineer materials for a very specific application. For example, some films have unique electrical properties. This type of films can be combined to produce microelectronic structures. The circuits, such as the microprocessor device shown here. Other films have unique barrier properties like being waterproof. For example, carbon nanotubes, which can be grown through CVD processes, are extremely hydrophobic. A water drop will bead up and not be absorbed by them. As shown here, these films can be applied to a surface as a coating to protect the material. Similarly, thin films can also improve physical properties, such as making a material resistant to scratching or other physical wear. The properties desired in the final application will dictate the type of film to deposit, which requires careful consideration of the material and operating preconditions for the deposition process. So this is the So physical deposition, and now we'll see the difference between physical and chemical deposition. The source is a solid material. In the physical vapor deposition, the source is a solid material in solid form inside the chamber with the substrate through physical processes such as in physical vapor deposition, the source is a solid material in solid form inside the chamber with the substrate through physical processes such as heating or sputtering. The solid materials form vapors which will coat the surface of the substrate. Chemical vapor deposition processes are different from physical one. Instead of forming vapors from a solid material within the chamber, gases are pumped into the chamber from an external source which react and cause the thin film to deposit. The primary difference between PVD and CVD is the means through which the vapors are generated. In PVD, the vapors need to be generated from a solid or liquid source, whereas in CVD, no new generation is required because the source is already in a vapor phase. There are notable differences both in deposition and material deposition and material properties between films deposited with PVD and CVD. In PVD, the deposition is generally more directional, meaning there is a defined path for how the molecules will deposit onto the surface. This can result in non-conformal films, meaning that the film may not contour smoothly along geometrically. This can result in non-conformal films, meaning that the film may not contour smoothly along geometrically complex surfaces such as trenches or rounded surfaces. By contrast, the nature of CVD processes results in multi-directional deposition, allowing for more conformal deposition along complex surfaces. Now let's go over some tunable parameters within CVD processes. To recap, the substrate is placed in a reactor under a vacuum. Source gases are pumped into the reactor which react with the surface of the substrate. This causes a thin film to deposit on the surface. External stimuli such as heat or plasma can be used to initiate or propagate the reaction, which causes the film to deposit. Gaseous byproducts will form as a result of the reaction and must be pumped out. There are many different types of CVD processes, but they all share the same framework. Within this framework, there is a wide range of variables that can be changed. CVD processes are categorized. Pressure inside the reactor. Some processes are more sensitive and require high vacuum, while others are not as critical. For this reason, there are different of CVD based on pressure. These include atmospheric pressure, low pressure, and ultra high vacuum CVD processes. Another way to differentiate CVD processes is by the stimulus used within the reactor. Most CVD processes will use heat to help the reaction propagate. However, some samples will degrade at high temperatures, such as polymers or biologic materials. For this reason, some systems use other forms of stimulus. This includes plasma-enhanced CVD, involves converting the precursors to plasma, and photo-initiated CVD processes which use UV light. There are also variations on how the sources are introduced, including atomic layer chemical vapor deposition, which introduces the precursor gases one at a time in sequence as opposed to all at once. So this is the basics of CVD processes. They have application in solar cells, in nanomaterials. Okay. So this is the difference between CVD and PVD. For the chemical synthesis, CVD is required, right? So I think this is for today. Okay, I hope you have enjoyed the class. You have understood what I have said. And still, if you have any question, please raise a question in the discussion forum. We will meet on next Saturday. Till then, good.